Very good. How are you guys doing today?
Good. How you doing?
I'm doing well, thank you. So let's just wait 1 minute and we'll get started. And I want to start with this slide. And this is a review for chapter 7. In fact, let me start with this. All right, good morning. Let's go ahead and get started. So these are the 11 chapters that we'll be covering in CS 285, and we're down at chapter 7. And just to let you know, the next 2 weeks are super important, not that the previous weeks weren't. But next week, we're going to be talking about VPN and IPsec, super important, widely used. And then week 9, we'll be focusing on ASA, Adaptive Security Appliance, a very popular appliance from Cisco that is widely used for lots of different purposes. So get ready for chapter 8 and chapter 9. And chapter 7 is the foundation for chapter 8 and chapter 9. And if all the stuff we cover this week makes sense to you, then we're going to have an easier time with chapter 8 and 9. And we don't have to stop and go back and review material from this chapter. So this is the big picture, and we're doing well on the timeline. And we'll talk more about this later on. So I think this is a good place to start with the review. So far, we've been talking about security in this course. We've talked about hardening devices. We've talked about firewalls. We've talked about intrusion prevention. We've talked about malware. And recently in chapter 6, we talked about securing the LAN with port security, trusting ports, not trusting ports, with DHCP snooping, creating that binding table that we use for other services like anti-MAC spoofing, anti-IP spoofing, and of course, we finished with STP. So all has been really great. This is one of my favorite Cisco courses. The one thing we haven't talked about is protecting the data. So how about the data itself? The most valuable part for any enterprise is the data. How about the data? So we want to secure the data, and we want to secure the data when the data is sitting on a disk, and we want to secure the data when the data is going over the network. And increasingly these days, the data is going over insecure public internet, right? Everybody, the public internet is not secure by default. And much of the data these days is going over the public internet. And we really want to protect that data. So let's move on to the one file I put together, just basically to capture everything that we cover in chapter 7. And if you have questions, please ask. So we talked about cryptography, and we said is a method of protecting information and communication through the use of codes. And I said there's nothing new. We've been doing this for several thousand years already. Of course, it's far more sophisticated now than it used to be by shifting, you know, the alphabets by 2 or 3 or 5 characters. And we have computers that can do amazingly sophisticated encryption. And we have computers that can amazingly break those codes. And we talked about the cryptographers, and these are the experts that develop the codes. And we talked about the cryptanalysts, and these are the experts that try to break the code. And it is the same skill set, except, you know, where are you focusing your energy? And oftentimes you need cryptanalysts to make sure that whatever the cryptographers come up with is good, right? Otherwise, how would you know? So we need to make sure that a cryptanalyst can't break that code. And the cryptography process, we start with plain text. So become familiar with those terms, plain text and ciphertext. So we start with plain text, which is this document. We're looking at it, and we put it through a cipher or an algorithm is the same thing, and then any key. And the key length is very, very important. And we've been talking about the importance of the key length in this chapter and in the previous chapter. And it's going to give us a ciphertext. And a ciphertext is what you call scrambled data. We scramble the data. And then we do the opposite to unscramble it. You know, we take the scrambled data, we put it through the same cipher algorithm, and then it will produce a plain text. So far, so good. So we talked about integrity, and we've used this term a lot already, and you will see it a lot over the next few weeks. And we're talking about data integrity, integrity of the data itself, whether it's sitting in a file or whether it's flowing over the internet. And we use hashing algorithms to do that. So hashing algorithms are commonly used to verify the integrity of data. In other words, to ensure the data was not intentionally or unintentionally. So I want to make this very clear. It's not always intentional. Sometimes it's unintentional. A 0 will flip to 1 or a 1 will flip to 0, and the file or the frame has lost integrity. One could use hashing to check stored data or transmitted data. Okay. So what's the hashing process? We take a message, okay, and the message can be encrypted or unencrypted. So don't confuse hashing with encryption. This is why we have this whole document. So we can separate each of the components, each of the Lego pieces, and then we can talk about them together. So we have a message, and then we have a hash function, and then it's going to produce a fixed length hash value, hash code, hash digest, hash key. It has lots of different names, okay? And that fixed length is also very, very important because we want to have very, very few collisions. And the longer the key, you know, the more possibilities we have, the fewer the collisions, right? So let's take worst case scenario. You have an 8-bit key, 256 different combinations. It's not going to take very long before you have collisions. And if you have a much, much longer key, let's say, you know, 256, okay, that is a much, much, much larger number. And the odds that you're going to have a collision are very remote. And that's what we want, because crypto analysts, the guys that are trying to break the code, are always looking for collisions to give them clues on how to break that code. Okay. And then as far as hashing algorithms, we said, you know, we have MD 1, 2, 3, 4 are legacy, obsolete. Nobody uses 5. We're still using, but look at the key 128, and that's not a very long key for a hashing algorithm. So it's good, but not very good. MD6 is out. It has some buffer overflow issue. It was never widely adopted. And then we have the secure hashing algorithm. Okay, the family. And we have 3 different generations, and generation 2 and 3, they give us a bunch of different key length to choose from. And before you say, I want to use, you know, 512 bits, you know, what is it you're trying to ensure the integrity of? And because there's a price you pay, right? Everybody, there's a price. I keep going back to this. So we always have to secure. It's going to cost me the most. Is it really that important? So, and I can't tell you what the answer is. It depends on the data you're trying to protect. So hashing issue, what if a bad actor changes the message and the hash digest, right, everybody? So what's to change? Because if they were to change one or the other, we have a problem. So if we have a bad actor, oops. Can you guys hear me? I got the message that my internet connection is.
Yeah, we can hear you.
Okay,
Hear
good.
you, yeah.
Thank you. Thank you very. Okay, let me know if that's not the case somehow. So we send a message and then we send a hash key, right? Everybody, they always go together. You always send the 2 together. You send the message and then you send the hash digest. Well, if one was to change one or the other, we would know we have a problem. But what if a bad actor was to change both? They changed the message, they produced a new hash digest, they send it along with the message. Well, as far as the receiver is concerned, everything is looking great. And that's because we're missing authentication. And what we want integrity with authentication to say, yep, this really did come from Zico, and yes, the message did arrive with integrity. And I don't think you want me to do this, but we've looked at the Ethernet 2 frame many times. It has a trailer, and the trailer is an integrity field, and it's 32-bit. Remember that discussion about how long do you want it to be? And the people that came up with the Ethernet 2 frame decided that this is good enough. They knew it's not very good hashing, right? Everybody, we know 32 is not very good, but they decided for this purpose, it's good enough. And they didn't want to use 512 because this is for each and every frame, and we're sending gazillions of frames back and forth. And they said, no, this is definitely more secure, but the tax is too high, and we don't want to pay that high of a tax. We just need something that is good enough, and they decided 32 for that purpose is good enough. Does that make sense? It's back to that CBA. Okay. And then we looked at five. They often use SHA, secure hashing algorithms, 256-bit hashing digest key. Okay. Any questions on hashing?
No, I reviewed some of it through the slides. I did go through to chapter 8 a little bit, but I'll save those questions for chapter 8 unless I figure some of it out. But
we'll cover chapter 8 is great, probably one of the best chapters because it covers IPsec, and IPsec is huge, and that's the focus for next week. And I was just working on the labs just to show you, and I think we're going to have some really great labs to work with next week. So this is what I've been spending my time working on, putting the labs together for chapter 8, because slides are wonderful, but unless you do a lab, for me, it's just going to fly out of my other ear. So I need labs to internalize what the slides told me. Questions on integrity? So we will get there, Frank, soon enough, next Tuesday. So let's talk about confidentiality. So confidentiality to ensure only the authorized people and or devices can see the message content. So we're trying to protect the content. Okay. Confidentiality is accomplished through encryption. So this is what we do to ensure confidentiality. We want to encrypt, scramble the data. So we have two different technologies, encryption technologies, symmetric and asymmetric. And please, let's make sure today this makes, excellent sense in your head. Symmetric is we're using the same key. So you create a Microsoft Word document and it has sensitive information and you want to scramble it, you want to encrypt it, and then you can encrypt it with a symmetric key. And if you want to read the document, it's going to prompt you for the symmetric key, which is a password, and then you type it in and then it will decrypt it. You don't know the code, you're not going to be able to decrypt it. And symmetric keys work wonderful. We love symmetric keys. They work very, very well. And a 128-bit symmetric key is fabulous security. It is excellent security, 128-bit. And 128-bit is not very long, everybody. When we talk about keys, especially when we talk about digital ID keys. So starting from the oldest technology is digital encryption. This is an algorithm, okay, which is 56-bit, and it's deemed to be very poor these days. And then they tried to extend the life of DES. So they said, what if we use it 3 times in a row? And that gave us the equivalent of 112, 168, which is very good. And then we have this really super popular algorithm called Advanced Encryption System. And it starts with 128, 192, 256. And like I said, 128 is very, very good symmetric key. It's an excellent symmetric key. It would take, years for a very fast computer to break that code using brute force. And that's pretty good. And then we have others as well. So symmetric encryption issue for network communication, if you have router A, router B, if you're sitting in a coffee shop and you want to log on to your bank account, how do you securely exchange that symmetric key? So we know they work really well. And for a file, it's sitting on your computer, You created the file, you gave it the symmetric key, and then when you want to open the file, you give it the symmetric key. Or even if the file is sitting in cloud storage, still it's the same process. It's easy. But now we have two computers involved. There is you, and then there is the server at the other end, you know, your bank server, your Amazon.com server, your Facebook server. How do we exchange that symmetric key? So that is the problem we have with symmetric key. Is, you know, are they going to call you? Are they going to send you a text? And there are security considerations with all of these different methods. So we invented asymmetric encryption. Requires PKI. I hope you've been reading up on PKI. Requires a digital certificate. The digital certificate consists of private and public keys. And the private key you keep, and the public key you share with the universe. You know, you put it out on the internet. And when the digital certificate is created, the private and the public keys are generated in such a way that what is encrypted with one key can only be decrypted with the other. If you encrypt with private, you can only decrypt with public. If you encrypt with public, you can only decrypt with private. That was the intent. And because of this unique mathematical relationship, those keys are really long. You can start with 512, which is useless. 1024, now we're going over 1,000, still very, very poor. 2048, it's considered good. So you need something 2048 or above, all the way up to 4096. And the problem with these super long keys is they consume a lot of resources to do their job, to encrypt or to decrypt. Remember, 128 symmetric is very good. And now we're talking 2048, 3072, 4096. Good, everybody, really, really long. And there is a price that we pay. And again, because of that unique relationship between the two, 1024 is a poor public key, is a very poor public key, and nobody uses anymore because it's very poor and easy to break. So we need 2048 or above. Very good. So we said this, all right. And we can use this digital certificate. We can use this private and public key for encryption. We just finished talking about that. For message authentication, okay, and the message authentication is say, yep, this message did come from Zico. It did come from Joey. Okay, for digital signature, which I said it stands in courts these days. So to say, you know, yep, this email did come from Zico because it was digitally signed by Zico. It couldn't be anyone else because only Zico has the private key, and it was signed by the private key. And signed by the private key means we created a hash, and then we encrypted the hash with the private key. Okay. So what we really need to do is we need to exchange that symmetric key. We don't really want to use those, even if you have a digital certificate yourself and the server has a digital certificate itself. We don't really want to use those long keys to encrypt every single piece of data that is going back and forth, because it could be a lot. And remember, we pay a heavy tax for the longer keys. So what we want to do is we still want to use a symmetric key, a much shorter key, but we want to securely exchange it over the insecure public internet. And then we use this private public key to do that. And since you and I don't have a certified digital certificate from a certificate authority, what we do is we are using the server digital certificate to do the symmetric key exchange. So every time you log on to, let's say, you know, your bank or your credit union, the bank or the credit union gives you their public key, and then the PC, the client, generates a symmetric key. They encrypt it with the public key, they send it back. And remember, what's encrypted with public can only be decrypted by private. And then the server will decrypt with their private key. And now the two parties over the worldwide internet, okay, have a copy, a secure copy of that symmetric key. And then we use the symmetric key for all the encryption, all the communications, because it's so much more efficient than those super long keys. Make sense? And I did say the exception is email, because email is asynchronous. We don't have a session. It's called a session key for a reason. And email is asynchronous. I send Joey a secure email. Well, he may read it, today, tomorrow, next week. And for that purpose, we're using our private and public keys. So we're paying the price, but we don't really have a choice with S-MIME or secure email because it's an asynchronous communication. Okay, so as far as asymmetric key algorithms, we have two. We have RSA that you've seen a lot and you will see much more of because it is the most popular and it can be used for encryption, methods, message authentication, and digital signature. Three different things. Everybody, encryption is one thing, authenticating that come from Zico is another thing, and then saying, yep, this was digital signed by Zico is the third thing. Okay, or DSA, and DSA is only good for digital signature. And like I said on Tuesday, I've never seen it. I'm not saying nobody uses it. I've just never seen it. So it's rarely used. Why? Because RSA does everything DSA does and much more. So why have two, one for this purpose and one for the other purpose? Have one that does everything you need, which is RSA. Questions on symmetric, asymmetric?
Not really. So I've been looking at a lot of the web pages certificates, and it seems like RSA is the gold standard of what everyone is using.
You got it. It is. I agree. Yep. And in fact, if you see DSA, let me know. I'd like to see one. I've never seen one. Everybody uses it. Okay. So RSA is an algorithm, and we have RSA keys, and those RSA keys tend to be long. And people are smart like you guys, and they've been able to come up with newer set of keys that are shorter. So we're still relying on the RSA algorithm. We just wanted to use the shorter keys. And these are the elliptical curve keys. And I will show you in a few minutes. Okay. So some people are beginning to move toward elliptical curve keys because they are shorter keys and they provide the same level of security. And shorter key with the same level of security is good because smaller key requires fewer resources. And now we can encode and decode very quickly. And back to router A, router B, okay, if they have to encrypt everything that is going between the two of them, and Ipsec will do that, and this is the focus for next week, we're going to have gazillions of packets going back and forth between router A and router B. And we want to be able to encrypt very efficiently. We don't want it to be slow. So if we can do it using a shorter key with good security, then great. That's what we want to do. So I talked about all of this. So let me show you a couple of things and we will move on. So I'm going to come back here. Let's stay with Net Academy, everybody. And you've seen this, more tools. Let me move this over here. And certificate, valid and trusted. Meaning, we went to the certificate authority that issued this certificate and we said, is this, a good certificate? And they said, yeah, we stand behind it. This is valid. And then we can take a closer look at the certificate, and we're using TLS. Remember, SSL has been deprecated. TLS is the new king, and TLS is an application encryption. HTTP doesn't encrypt, HTTPS does, and the S stands for SSL, except SSL has been replaced with TLS. I know it's a lot, but we've gone over this many times before. And all of this makes sense. So this is version 1.2, 1.3 is the latest. EC, everybody, EC is elliptical curve. Remember those newer, shorter keys that give us security with a smaller key? That's what the EC for. And DH is Delhi-Hellman, which we will cover later on. RSA is, we've been talking about it, 256-bit key. And AES is advanced encryption, 128-bit key. So this is what all this jumbo stuff means, and you can copy it and paste it into Google and they will tell you what it means as well. And this certificate was given to s3.amazonaws.com. So it's being hosted by Amazon Web Services, and the issuer is DigiCert. Okay. And it's valid from this date to this date. And we can come over here, and for encryption, okay, we're using, for hashing, we're using SHA 256. And for digital signature, we're using SHA 256 RSA. Here, RSA again. Here, RSA again. This is the keys they're using. They're using an RSA key. And remember, 2048 is the bare minimum you want to use these days. And just to show you another one, I'm going to go to Google. And I'm going to come here, and I hope you will do all of this in your own. And valid and trusted, encrypted, blah, blah, blah. Very good. And then let's look at the certificate. Google.com, issued by CA, Certificate Authority. Okay, SHA 256, 256 RSA. And these are the elliptical keys, everybody. 256-bit key. And this 256-bit elliptical curve key is more secure than 2048. And this is relatively new, It's just I don't know the math. I don't understand the math. I don't think I will. It's going to go quickly over my head. All I know is an elliptical curve key, okay, is much shorter than an RSA key and provides equal or better security. Okay. So let me show you one last thing and we'll move on. So if you have a Windows Professional and above, 7, 8, 10 or above, you can, let me come here. Let me nuke this. And let me create a new folder called Top Secret. And I'm going to go to Properties. And I'm going to go to Advanced. And I can compress or I can encrypt. And to encrypt, to use file encryption, which is what this is, you need a digital certificate. And if you don't have one, then Windows will create one for you. Just remember, the one that Windows will create for you or the Cisco iOS will create for you cannot be verified by a certificate authority. So you're not going to be able to use it out in the internet because it was generated by you on your own computer. However, for my purpose today, this is good enough. I just want to be able to encrypt files on my file system. So I'm going to say, okay. And now it's encrypted, and I'm going to come in here and create a new file, Microsoft Word, test. And let me show you, everybody, view extra large. You see this lock over here? This is telling me this is encrypted. So I can open it up. It's not going to prompt me for a password because it's not password protected. I can type whatever I want. I can save it. Okay. It's never going to ask me for a password as long as I'm logged on as administrator, because I'm logged on. If I was to log on as Zico and try to open this file, it's going to say, sorry, no can do. Okay, you don't have permission. And here I'm not relying on the access control list, because that's another way of handling security. I'm just relying on this file being encrypted using the admin digital certificate. And I've talked plenty about MMC, everyone. And I'm going to add certificates. And lots of, remember, we have to manage these certificates. These are the trusted root, okay. Trusted publishers, but let me come to personal. And this is the certificate I just created, everyone. And please do this on your own computer. So your computer is quite capable of generating a digital certificate for you. Just remember, it's not going to be honored by anybody except you. And if I was to double click on it, okay, issued to admin from today until 2120, okay, and detail SHA1, which is poor security. Do you guys remember? That's the first edition of SHA. So that's 160 bit encryption. RSA is RSA, and RSA 2048 bit. So it's not the most secure. I mean, this is good key, but SHA1 is relatively poor security. So it's not the most secure, but again, back to CBA, what are you using this for? And maybe for what you need it for, it's good enough. And if I want to, I can export it. And do you want to export the public key? Do you want to export the private key? Do you want to export both? So if I want to use it to communicate with Frank, I have to send him my public key, and I can export it into a file and send it to him, and he would import the file, and now he has a copy of my public key, and he would do the same. And then for backup purposes, I want to export my private key and then save that file, because if something bad was to happen to this certificate, guess what? I can no longer view the files that were encrypted with it. So I hope you can do this in your own, and I think you will learn a lot by doing it in your own. And this is Microsoft Management Console, MMC. Just type MMC and it would run. Okay. Any questions on this? Have you guys done that?
Yeah, I've done it for a couple documents, and we did it in one of our classes with you a while back. I don't remember what it was, but we've done
maybe 140.
Probably, yeah.
Okay. Okay, excellent. So let me see where we were. So we talked about integrity, and we talked about confidentiality. And please separate, okay, the two. Integrity is integrity. Confidentiality is confidentiality. Integrity is hashing. Confidentiality is encryption, symmetric or asymmetric. And every day you go to Gmail, every day you go to Amazon, every day you go to Facebook, every day you go anywhere in the internet. Okay, we are using that private public key to exchange a session key. That's it. We're not really using it to encrypt, decrypt. You don't have a digital certificate yourself. I'm going to assume that. But we're using the server digital certificate to securely exchange the session key, and then we're done. We're done with the digital certificate, and then we use the session key for the rest of that session. And it's short, it's symmetric, it's efficient, it's fabulous, and it makes sense. Authentication to verify you are who you say you are. Authentication can be a single factor or multi-factor, and we're moving toward multi-factor. I'm trying to do multi-factor for everything I do. Something in your head, something in your body, or your body itself. I have a Schwab account, and I've been using a token. Everybody, something in your body. This is my Schwab token. And for the last few months, they've been wanting to add my voice for authentication. It's like, yep, go ahead, log on with your account password. Yes, use your token and say something. Repeat this sentence, because they want to. So this would be, you know, 3-factor authentication. Account, password, token, which is very, very good, just 2-factor. And now Schwab is saying, Zico, you have so many billions of dollars with us. You know, we want to make sure this is really you. And we want to use your voice as an additional way of authenticating you are who you say you are. And the more factors, the better. And modern operating systems hash the password. We know that. So integrity, confidentiality, authentication. So let's talk about message authentication code. And you will see this next week, everybody. Okay, there's nothing here that you won't see next week. In fact, I'll show you this one slide, the only slide I want to show you from next week. 285, because next week is going to be great, and slides and the IPsec. Okay, confidentiality, integrity, authentication. We'll talk about DH later on. Okay, and over here to establish some of the authentication, we have to use HMAC. So I could easily put HMAC as another box next to PSK and RSA. It's not here, but we will be using it for that purpose. So we want to authenticate that the message not only has integrity, but it came from Frank. Everybody, so Frank and I are communicating. He is using hashing to let me know that this message is going to arrive intact. Well, that's great. I want to know it arrived intact or not. But I also want to know it came from Frank. And we do this by agreeing on a key, pre-shared key, pre-shared secret key. And then he would add the key at the end of each message. Let's say he's going to send me 100 messages. He will add the key to the end of each of these 100 messages, and then he will hash the whole thing, the message along with the key. And then he will send me the message without the key, because the key is a password, it's secret. And then he will send me the hashed value, the hash digest. And then when the message arrives, I will add the key to it, because it's a pre-shared key, and then I will hash it, and then I will compare it to the hash digest that Frank sent me. And if they match, it has integrity and it came from Frank. And a bad actor, to do this successfully, they would have to have that pre-shared key. And of course, we didn't share it with anyone. We kept it between the two of us, and no one else knows about it. So this is what MAC is. MAC is I want to verify the authenticity of the message, not the integrity only, but I also want to be able to authenticate. And HMAC is we're using hashing for that purpose. What is it we're hashing? We're hashing the message along with the pre-shared key. Make sense, everyone? So now we're mixing. Now we're saying, okay, we need a protocol that is going to give us integrity and is going to give us authentication. Authentication plus integrity. DH, okay. Diffie-Hellman, from now on just DH, okay. So this is a protocol that's going to enable us, I will read it, okay. Key exchange method allows two parties that have no prior knowledge of each other, you and Amazon.com, you and Twitter.com, to jointly establish a shared secret key over insecure channel, like the public internet. Okay. And to come back to this one slide over here, and this is it, DH right here. And there are many, many different versions of it, from 1 to, I think, 24, 25 today. And the newer versions are more secure, and they accommodate a bigger key. So DH1 can only accommodate a small key. DH24 can accommodate a much larger key. That's really the big difference between 1, 2, 5, 17, 24. Okay, so this is next week, everyone. It will be a great discussion. Okay. And here, they're showing us the different DH keys and the size keys they can accommodate. Any questions from this document? Integrity, authentication, authorization, message authorization, and DH for key exchange.
Not for the document, but I do have a question about some of the, the labs for the entire security thing. Is there more packet tracer labs out there than what's provided with the from Netacad? Because so the one that we did for this week was good, but I'd like it if, there was more of them where we practice more implementation, because I can keep redoing the same one, but it's kind of like.
Which chapter are you talking about, Frank?
Well, for 5 for now, since that's what we just finished.
Okay, so I don't always share all of the, I don't ask you to do all of the Net Academy packet tracer labs. So there's probably more. And you can find out from Net Academy itself if there are more Net Academy labs, but I can tell you really quick. So let me see. Old.
Yeah, there's only one for 5.
5.
And it's the one that we did.
Yep, there's just one. You're right. And the other one, there's another one, except that's on real equipment. So not 5411, that would require real equipment. So there's just one.
So just keep for chapter 5 at least. Keep working with that.
That's all we can do.
Okay.
I mean, you can look at 5411. However, if you don't have real equipment, if you don't have physical equipment, you're not going to be able to do it because it's way beyond the scope of what packet tracer can do. But you can certainly look at it and see if you can do it on a piece of paper. But that's all we have in Net Academy for chapter 5.
Okay. That's what I mean, I looked on the packet tracer index, and that's all I saw, but I wasn't sure if like you knew where more we're at, like if I don't know.
Nope, that's it. That's all I have right here. That's all they included for chapter 5. So I want to look at some slides, everybody, and I'm going to go through those slides quickly and let me know if you have questions, okay? Some authentication, integrity, not interested. Okay, cracking codes. There are several different ways to do it. Brute force is quite popular. Guessing is quite popular. Dictionary attack. And then if you are a crypto analyst, remember a crypto analyst is a person that's trying to break the code. You know, there are some other methods that they can use. You know, like the most valuable piece of information they're really going after is those collisions. You know, can we use 2 different strings, 5 different strings that can produce the same key? And if you can do that, half of the battle is over. Okay. We talked about cryptography, cryptographers, and cryptoanalysts. NSA is really good to know, everyone. You know, there are lots and lots of institutions and organizations out there. NSA is a US government agency, national security agency, the premier cybersecurity agency on planet Earth, with many, many crypto analysts and cryptographers and supercomputers, and a 30 billion annual budget, something like this. So a lot of money to do what they need to do. And they spy on everyone, not just the Russians and the Chinese, but you and I as well. We talked about MD5, and we know there's a family of SHA. We've talked about DES and 3DES and AES, and I said, keep your eye on AES. You will see this acronym over and over. And here, you know, we're using both to authenticate. This is, you know, you see HMAC, everybody? HMAC. Okay. So this is hash message authentication. And you can see we are doing hashing. So are we doing MD5? Are we doing SHA1? We've covered RSA and we've covered DSA, and we said we use DSA only for signature. Okay. So why is this useful for authentication? Because you can digitally sign something with your private key, And I want to show you really quick, and I've shown you before. So this is why this is in this category. This is why RSA and DSA are in here. Because if you digitally sign something, you're telling the world, this really did come from me. And we'll come back here. Program files, Google. And let's do this one. Digital signature. So we hashed with SHA, and then we signed with this certificate. Everybody? So we hash and we sign. It gives us 2 things, integrity and authentication. So this is what that does. We can do it with HMAC, or we can do it with a private key. Both of them accomplish the same goal. And this is why we have RSA and DSA under authentication. Are we good there? And then you decrypt with the public key, and you say, yep, this really did come from Frank. Okay. So I explained what hashing does, and I think this is good enough for me, for us, is that we have a plain text, we put it through a hash function, and then it produces a fixed length. And we talked about the importance of the key. And here they are showing us examples, okay? And I think one thing they are trying to tell us here is pay Alex $100. What if a bad actor along the way said, no, pay Zico $1,000? And they changed the hash key. Well, you know, what we're missing from here is authentication, right? Everybody, what we're missing is authentication. So authentication is really, really important, and we want it to go along with hashing because we want integrity and we want to know it came from. Okay. Yep. And MD5 is 128, SHA is 160-bit key, and SHA 256 is 256-bit key. So the same plain text, this is the plain text, it's producing a larger key because MD5 always produces 128, and SHA1 always produces 160. And we already talked about the importance of a longer key. We have fewer collisions. SHA 256 is far more secure because it's 256-bit, gazillions and gazillions of combinations, and the odds that we're going to have a collision is much, much, much smaller, and it makes it much more secure. And we talked about, do you really need 256? Because there is a tax that you pay for 256, and we can go back to Ethernet 2, and they decided 32, which everyone says is highly insecure, but these guys said, look, it's just a frame. We're just trying to ensure the integrity of the frame between switch 1 and switch 2. And for that purpose, 32-bit is good enough. And I agree with them. Okay. Message authentication code, everybody. So we take the plain message and we add the secret key, the pre-shared secret key, and then we hash the whole thing. And now we have integrity and we have authentication. You see those two pieces? This is the authentication and this is the integrity. And we need this for next week. Okay. And Cisco products use hashing a lot. If you remember when we had router 1, router 2, and router 3, and they wanted to authenticate each other, and the three of them share a pre-shared key, the same pre-shared key, then you know they can use hashing and message authentication code for authenticating, because we did say sharing the network map with a bad actor is a bad thing, and we want to make sure that this is a legitimate device we're sending routing information to. So we want to authenticate, and that's how we authenticate. Yep, this makes sense, and I said this is also true for your credit card, everybody. So credit card generation, verification, we don't really need to worry about the key exchange there. Okay, lifetime. But for a digital certificate, we have to generate, and we already talked about the unique relationship between mathematical relationship between private and public. We verify by going to the certificate authority that issued that digital certificate and say, is this valid for this purpose? Key exchange, you know, we need to share the public key. Okay, the private key you keep, but the public key storage, where are you going to put it? And you know, your PC has a database, and I showed you an MMC, everybody. So there's a database with all that stuff. Allow me to show you one more time. I should keep it running, but maybe it's good so you can see how to do it. And trusted, everybody. So these are the root certificates for these different certificate authorities, and we have to keep this information somewhere, and this is the database and the GUI for you and I to see what's in the database. Okay. Lifetime, they have a lifetime. Usually it's a year, but it can be shorter or longer. And yes, you know, if something got compromised, we want to let everyone know this is being compromised and don't honor it anymore. The same is true for your credit card. Okay. And now we're going over the different algorithms, advanced encryption services, everyone, advanced encryption standard, advanced encryption standard, and it supports 3 different key lengths, okay? Time to crack, I'm assuming they're talking about 256, 149 trillion years. So you can see 128 is, well, they didn't talk about 128 here, but 128 symmetric is very, very good. 256 is crazy good for now. And here they're trying to explain the relationship between the length of the key and the security. And all they're saying is the longer the key, the more combination, the more secure. And yep, this is good. This is a great slide, everybody. Okay. Symmetric, asymmetric, digital signature, hash. Nobody uses an 80-bit symmetric key, but they're saying even 80-bit is good for 3 years. 128, it's good for 30 years. And if this is a session key, you know, how long are you going to stay connected to that server? You know, 1 day, 2 days, 5 days. So 30 years is a very long time. But then look at the relationship between symmetric and asymmetric, everybody. They are telling us an 80-bit symmetric is equivalent to 1248 asymmetric. Okay, 128 is equivalent to 3248 asymmetric. And there's a huge difference between these two. 128 is a gazillion times more efficient than, it's not gazillion, but this is a zecogazillion, than 3248. And this is why when you are connecting to a device, you really want to use symmetric for the bulk of encryption and decryption. You don't want to use asymmetric because it's far less efficient. And then if you want to digitally sign, 128 symmetric is about 256 and about 256 for a hash. This is a great table. I like this table. Confidentiality, right? Encryption, very good. It is encryption. Symmetric, asymmetric, I'm not sure there's much else to say here. Okay. Here they're talking about the elliptical curve keys, the newer keys, the shorter keys that give you good security. So you don't need to go to 4096 to have excellent security. You can use a much shorter key that will give you the same level of security. And they're explaining it. This is super old, everybody. Okay, nobody uses anymore, but not too long ago, that was the only thing that was allowed by the US government for you and me, except they've lifted those restrictions. So they don't have restrictions anymore because no one honored them anyway, and it was impossible to enforce. And we live in a digital world where everybody is using the internet for everything, and we wanted to do it securely. I'm skipping over these. It's just another encryption algorithm. Okay. Diffie-Hellman, this is really important, everybody. So this is a protocol we use to securely exchange a key among 2 parties that want to communicate. So next week, we'll talk about Ipsec that is super popular. And you want to create a VPN between router 1 and router 2, let's say site A and site B. Okay, and we certainly don't want to use the digital certificate for encryption and decryption, even though we can give router 1 and router 2, site A and site B, digital certificates, and we can use those for encryption and decryption and everything else, except they're crazy long. So what we want to do is we want to use a symmetric key for encryption, decryption, and we need to securely exchange this key between router 1 and router 2. And this is what DH does. They say, okay, we can do this for you securely over the insecure public internet. And now both of you have the symmetric key. This is what you use to encrypt. and they're talking about, okay. IKE is Internet Key Exchange, we will use next week. This is a very important part of IPsec. So you will see it again. We said SSL has been deprecated. We know SSH instead of Telnet. We are encrypting the communication between the client and the server. And it all started with pretty good privacy. If you really want to learn more about private public or PKI, this is a good place to start. Google pretty good privacy or just PGP and go from there. And there are lots of tutorials and you will learn a lot because it all started here. And now we're using it many, many times, you and I and everyone else, many, many, many times every single day. Okay, so we can also authenticate everybody. So when we talk about authentications, we've talked about two methods. We talked about MAC, message authentication code, where we have a pre-shared key and we add it to the message and then we hash the whole thing. And we can also use private and public key. And for authentication, you hash something and you sign it with your private key. You encrypt it with your private key. This is the same thing. Sign it, encrypt it with your private key is the same thing. So to go back to secure email between Joey and myself, and we both have an S-MIME capable email client, and we each have a digital certificate, whether it's home generated or it's from a certificate authority. And I have his public key and he has my public key. And I want to send him something I want to encrypt, I will use his public key. If I was to use his private key to begin with, I don't have his private key. And let's say, he encrypted something with his private key, everyone can decrypt it because everyone has his public key. So it wouldn't really be confidential. But if I was to encrypt it with his public key, he's the only guy that can decrypt it. And if I want to tell him this really did come from Zico, it didn't come from anyone else, then I will sign it with my private key. So I'm using public for confidentiality, and I'm using my private key for authentication. Make sense, everybody? His public key for confidentiality and my private key for authentication. And secure email is on the rise. Okay, it's becoming very, it's already popular among financial institutions, and I think it's coming to you and me. Eventually, we're all going to have a digital certificate, and we will have the option to encrypt our email messages. Because if you're using Gmail, everybody, okay, Gmail is reading your email. You all know that, right? If you don't believe me, here, I'll show you. Everybody, stay with me for a second. Compose to Frank Lister test. Everybody, please read attached file. Good, everybody? And now I'm going to send it. Did it send? Usually it says, oops, you forgot to attach something, right, everybody? So that's usually what it does. So I'm not sure why it didn't do it today. Well, how did Gmail know I didn't attach a file if they didn't read the content of my email? So Gmail and everyone else, they read the content of your email. And if I don't want them to read the content of my email, I only have one option. And that one option is to encrypt. And this is why encryption is going to become very, very popular, because we really don't want all these different services reading our email.
So that brings up a question for me, because part of them providing a free email service is that they read the emails and they use the metadata to provide advertising. Yep. Exactly. And so if we're encrypting it, then does the day of free email accounts go away?
I don't know, but they're not going to get as much value out of that account. And I agree with you. And it's really scary, because sometimes I will send an email and talk about, I'm looking for a new car, and then I start getting car advertisements, or I say, you know, I'm looking for a new TV, and I start getting TV ads. And it's like, that's how they found out. Okay, it wasn't random that they are sending me those ads. You know, they're scanning my email. Oh, he's shopping for a car. Let's start bombarding him with car ads, or whatever it is you're shopping for. So we want to deprive them from that. And that's the only way to do it, is to encrypt. And the technology is here. We just have to start using it. And as digital certificates become the norm, you know, everyone's going to say, yeah. And we figure out how to do it, because all these clients are capable. We just have to configure the other person public key. We just have to add the public key to our key database, and then we can begin to exchange email securely. Okay, I'm going to move on. Symmetric. Okay, so here we are with DH, everybody. Okay. DSA is digital signature algorithm. RSA, we start with 512, but I already said 2048 is the bare minimum. And this is saying it goes up to 2048. This is really old. It goes up to 4096. So we have 2048, 3072, and 4096. And of course, what they're not showing us in here are the elliptical curves. So this is a bit old. This slide is a bit old, because we have newer, more sophisticated keys, and those are the elliptical curve. And everyone make a note, please. Could you please make a note? Okay, go to Google, we're done with this. And then just type elliptical curve. Okay, no, not this elliptical curve. Here you go. Okay, and then just read about it. Just educate yourself on elliptical curve, because it's gonna become the gold standard. It's not yet, but it's gonna become the gold standard, because who wants to use a 4096 key if you can accomplish the same security with a much shorter key? Makes sense, right, everybody? So you're getting the same level of security with a shorter key. It's like buying the same product for half the price. So why would you want to pay full price if you can buy exactly the same product for half price? So elliptical key is becoming popular, and it's going to become much more popular because it gives us an equal level of security with much shorter, much more efficient key. So educate yourself on it. And oftentimes you will see it as an EC. EC here, I'll show you, because this is encrypted. So more tools, blah. Okay. You see this over here, and you can Google this. This is an elliptical curve key. And sometimes it will say EC, but this is an elliptical curve. So they're using elliptical curve. So it's becoming very, very popular. So you may as well educate yourself on elliptical curve. So every time you see the terms, like, okay, I don't understand the math, but I know what the objective is. And I don't understand the math either, nor am I interested in understanding the math. I just want to know what is it, and you know, what are the benefits and what are the issues. That's usually what I focus on. Digital signature. Okay, we talked about that. You hash, and then you encrypt with the private key. Okay, and now they're talking about certificates. Okay, so Bob got a digital certificate, has a private and a public key, and Bob will share his private key with everybody and keep the private key to himself. And we're back to RSA and DSA, which nobody uses because it only does signature. RSA does signature, authentication, and authorization. Now, encryption and authentication. Very good. Public key, PKI. This is another thing you need to educate yourself on. Okay, so that's where you would go. You would go to one of these certificate authorities to obtain a digital certificate, and there's a bunch of them. VeriSign has been around for a long time, and they're excellent. Symantec, DigitCert, there's many CAs out there. It's a service that they provide. Okay. The different classes. Okay. And these are services that will use the PKI, SSL, TLS, everybody, IPsec next week. S-MIME, we just finished talking about it, secure email, and TLS. And EAP is an encryption protocol. So this is an encryption protocol, which we will always talk about next week. It's one of the IPsec protocols. EAP is one of the 3 IPsec protocols, which we'll cover next week. Certificate authorities, okay. So you would go to authenticate. So remember when we were here, everybody, when we were here, and it said valid and trusted. Well, who said valid and trusted? So we took this certificate and we went back to the certificate authority and they said, yep, it's valid and trusted for this purpose, which is, you know, going to their website. Yep, it's valid and trusted. That is chapter 7. Questions? Integrity, okay, confidentiality, authentication, and then the mixing and the matching. Mix and match. We don't just want one. We don't just want integrity. We want integrity and authentication. We don't just want integrity. We want integrity and confidentiality and authentication. We want all of them. Or we're only interested in encryption. We're not really interested in integrity or in authentication. We just want to encrypt. This is what you do when you encrypt your Microsoft Word file. You're just encrypting. And if you know the symmetric key, you're good. Questions?
I think I asked most of mine or whatever through the lecture.
Does this make sense?
Yeah.
Okay. So next 2 weeks, everybody, next 2 weeks, where is it? Right here. So next week is VPNs with IPsec. And let me show you IPsec really quick. So you've seen this a gazillion times. And we have SSL, which is deprecated, and TLS we've been looking at today. And this is an application. It's one protocol, and it has to be called by the application. HTTP doesn't, HTTPS does. Telnet doesn't, SSH does. So the application has to decide if they want to encrypt or not. Okay, IPsec is down here, layer 3, which basically means it doesn't matter what the application wants, I'm going to encrypt, because everything has to go through layer 3 in the way out and layer 3 in the way back in, right, everybody? And everything is going to be encrypted. And if it's already encrypted, no big deal, we'll encrypt it again. We do this all the time. We encrypt, decrypt multiple times. As long as you do it in the right order, it doesn't really matter, because it's just a string. A string is a string. So the encryption algorithm is going to say, oh, this is already encrypted. It has no idea it's already been encrypted. It's just a string of zeros and ones. So from an algorithm point of view, it's just a string of zeros and ones, and I will be happy to encrypt it for you. The fact that it's been encrypted 5 times before, it doesn't really know or care. It will encrypt it again. And IPsec is a framework. Sometimes I use the term buffet. And you get to choose. Remember ESP, everybody? I said we'll see ESP next week. Well, this is ESP. And I'm not going to get into it now. We'll get into it next week. But it's going to be a big, important chapter. And I'm refining the labs, and I will have them done tomorrow, Saturday, put them on the Google Drive, and we will have labs to do to reinforce the learning. And IPsec was designed for IPv6. IPsec is built into IPv6, and it can also be used with IPv4. But it's built into IPv6 protocol. And the genius of it, again, don't want to get into chapter 8, is you can see it is a buffet. And next time there is a newer hashing algorithm, we just put another box here. And it still is IPsec framework. We just have a new algorithm on that buffet table. And if there's a new authentication algorithm, they will just add it. And this is the genius of IPsec. And this is why IPsec will be around for a very, very long time, because it's not a single protocol. It is a buffet, and we can add dishes to the table, and we can remove dishes from the table over time. Questions? We're good?
I believe so.
Okay. There's no packet tracer labs for chapter 7. There's like, Google and research and type the answers in here, but there are no packet tracer labs for chapter 7. Okay. Very good. Everybody will have a wonderful rest of the week. And we'll see you on Tuesday to talk about VPN and IPsec.
Sounds good. Have a good weekend, Zico.
Okay. Goodbye, everyone.
Yeah, that wasn't much too difficult to understand. I just it's gonna be difficult for me to just remember it.
Okay.
Right? Yeah.
Okay.
But yeah, thank you. Thank you.
You are most welcome, Robert. We'll see you on Tuesday.
Yep. Or Monday.
Monday, yes.
For the.
Yep. We'll see you Monday.